Thank you. Thank you for the introduction. Thank you to the organizers for the invitation. And yes, I come from the British Museum. And with this presentation, I would like to give a brief overview on a couple of projects that we have worked on in the last couple of years. And the focus will be on textiles from Egypt, ancient Egypt. But I am a scientist, I am a chemist by training, so I would like the focus of the presentation to be actually related on the analytical protocol that we apply at the British Museum wherever we are asked to investigate a textile. And this analytical protocol is actually a joint effort that I put together with my colleague Joanne Dyer. And we have different expertise. I am a mass spectrometry person. She has a more spectroscopic and imaging background. And so 2-3 years ago, we started this idea of wanting to figure out what we could do non-invasively on textiles, so without taking samples, and how we can use the information that we can gain in this way, so without taking samples, to have a strategy and select a very small number of samples that we can then take and analyze distractively by liquid chromatography mass spectrometry to identify the natural sources of the dyes. And so the first project that we worked on in this perspective was the Late Antique Textiles project. It was not new. It was building on a couple of projects led by Elizabeth O'Connell, and they were based on excavation work in Antinopolis and Wadi Sarga, which are two very famous ancient Egypt excavation sites. And some of the star objects in the British Museum collection from this site had already been exhibited in several occasions. And after the exhibitions finished, we had the opportunity to analyze and investigate some of these textiles. And the star object has probably always been this little child sock. It's almost 2,000 years ago, but it looks like it was made yesterday. And we also could analyze, together with the sock, 3-4 pieces. I show three here. And these were furnished in textile fragments from Wadi Sarga, slightly later period. So with this particular project on late antique textiles, we had the opportunity to work a little more in detail on multispectral imaging. Multispectral imaging is not a new technique. It has been applied to paintings, to polychrome sculptures, but there is not much work that has been done on textiles. So we wanted to see what the potential of the technique was in application to this type of textiles. The principle is quite simple. You have an illumination source, which can be a white source or a UV source. The light interacts with the materials that are in your objects, and it interacts in different ways. It can be reflected, it can be absorbed, it can induce emission from the materials. And then you have a camera, which is a simple camera, which can just record at a quite wide range of wavelengths, and you can use different filters on the top of the cameras to select specific wavelength bands. And these are just images of the setup when we were imaging the sock. So the sock was a very nice object to start with, because it has different colors, but different shades, but the areas are quite defined. There is not too much overlap between the areas, so it was not, let's say, a confusing object to start with. And the first image that you can probably get, one of the most informative with multispectral imaging, is the so-called UV luminescence image. And the the interpretation work is done by comparing the colors exhibited in the under the two different lights. So this is a comparison between the visible and the UV. And if you start looking at, for example, at the red areas, you can see that most of them show this typical pink luminescence under the UV, and this is usually a first indication of the presence of matter. Of course, multispectral imaging is not a strong identification technique. The identification has to be confirmed in first place. And so we used fiber optic reflectance spectroscopy, which is another non-invasive technique which uses just the reflected light to produce fingerprint spectra. And you can see here, these are all spectra pointing towards the presence of a plant-based red dye. And so all the red areas in the sock were likely to be dyed with madder in this case. So instead of sampling all the red areas at this point, we took just two samples, one from a lighter color and one from the darker color. And by looking at them under the microscope, we could see that there was a difference in shade for sure. And then the HPLC-MS confirmed the presence of madder. It's always difficult to say the exact rubia species of the madder when you are in front of very old samples. But the interesting thing here was that the two samples didn't show enough difference to justify such a difference in color based on a different source of madder. So the profile of the molecules was very similar. So we thought that maybe there was a different mordant, but when we did scanning electron microscopy with EDX, we saw that the EDX spectra were very similar. The aluminium peak was quite high, and it pointed to the presence of alum in both samples. And so what we think is that here we are simply in front of a higher concentration of madder in the darker sample and a lower concentration of madder in the lighter sample. So it's a dye bath. It's a multiple, probably, dye bath effect. And then going on with the interpretation, you can see here I have highlighted the green areas that also show some different behavior under the UV light. And similar things can be said for the purple areas. But another image that can come into help, especially with the green and the purples and the blue, is the infrared false colors image. And the reason why is because indigo appears red in this image. And so pure indigo was showing red, but when indigo was mixed with a red source, it was appearing orange. So all the purple stripes were actually orange in the false color images, whereas when it was mixed with a yellow, it was appearing pink. And so all the mixture between indigo and yellow were pink in the false colors image. And so this was already an indication that indigo was present in all these mixed colors. It was again confirmed by force. So we did the reflectance spectroscopy, and these are the spectra indicating the presence of indigo. And again, we could select just a few samples, not all the areas. The presence of indigo was confirmed by LCMS again, and we could also identify the source of yellow, which was a luteolin-based dye. And finally, the semi-DX showed that the blue fibers, in this case, we were mostly in front of mixed fibers in the same thread. So the blue fibers were not mordanted, whereas the yellow fibers were mordanted with alum. And a very similar situation for the purples. So the fiber optic reflectance spectroscopy highlighted the presence of indigo and madder. We took two samples which were showing fibers dyed with different colors. And the confirmation came at the molecular level with with HPLC-MS, and same thing for the semi-DX, where we saw that the indigo fibers were not mordanted, of course, and the red ones were mordanted. As I said, we could analyze other textiles, not just the socks, so we could test the method on a more difficult pattern, because you can see here you don't have these very nicely defined areas. The results told us that the palette was very, very limited, so we could find only mud, indigo, a source of yellow, which was a luteolin-based yellow, very consistent with weld, but yeah, there is discussion about weld being used in ancient Egypt. And then in the furnishing textiles, we found tannins for the brown. So four base colors to obtain all the shades that they were obtaining in these textiles. And finally, with our work, we managed to kind of give this decision scheme, which is comparing all the colors that you can see in the various multispectral images, which are not just the two that I showed, there are more. And so comparing all these colors, you can hypothesize the presence of a colorant non-invasively. Now, I don't want to send the message that multispectral imaging is enough to identify a color. This was a work that was possible by confirming all the colors with liquid chromatography mass spectrometry, but then the interpretation can go back, and so once you have done it once, you can then have your strong base to then analyze another textile and use the decision scheme without taking samples and taking a very small amount of samples. We published the work in PLOS ONE, is open access, so if you want to know more, you can look at the article. And now, with the second case study, I would like to talk about some unpublished research that we have done very recently in collaboration with the Egyptian Museum in Turin, in Italy. And in this case, we focused on mummy shrouds. So the question here was why some of these red shrouds were still keeping a bright red colors, whereas there are some mummies where the color is quite faded, and in other cases the color is almost completely faded, and you can see that it was colored only by looking underneath the bandages of the mummies. So we selected a series of mummies from the British Museum and from the Egyptian Museum in Turin, and these are some of the ones that we selected, and you can already see here how the bandage on the left is very red, whereas red is difficult to pick in the other mummies. And in this case, the analytical protocol, the idea was similar. We couldn't use the multispectral imaging because of the dimension of the mummies, which are very big, and so it was a bit tricky. But we used some microscopy with visible and UV light instead. And it was immediately clear, using non-invasive reflectance spectroscopy, that we were in front of three sources of red. One was not an organic dye, it was a mineral pigment, so it was hematite that was applied on the still very bright red textiles, whereas a source of madder and safflower were used in the most faded situations. We could use the force to take many measurements, and then we selected just a few samples again, and we could look under the microscope. So this is a visible and a UV image, and in the UV for the hematite you can see the distribution of the particles on the fibers, which absorbs the radiation. And this was nice because it was indicative of a fine distribution of particles, which appeared to be consistent, which is referred to as the smearing method to this mud bath that is reported in written sources to soak textiles in hematite, in red earth. The presence of iron was confirmed also by X-ray fluorescence. But then when we looked at the mother samples, we started to see something that, I mean, as I said, this is unpublished research, so we have an interpretation for this, but I'm very open to hear other opinions. And so in this case, we could see these, especially under UV light, these agglomerates, these big particles of color that were exhibiting the UV luminescence. When we did the analysis by LCMS, we could confirm the presence of mother. There was some differences in the relative amounts of the various molecules, and we picked up the presence of tannins as well in all the samples containing mother. But then also when we looked with scanning electron microscopy, you can see here, this is the same big agglomerate that we were observing under the UV light. And when we did the EDX there, we saw that it was a high concentration of aluminium, so it was rich in alum. But then the color was not distributed on the fibers as we were used to see when a fiber is dyed with mother. So we think that here we could be in front of a situation where the mother, the alum, and the textiles are put together in the same dye bath instead of pre-mordanting the fibers with alum and then dyeing with mother. If you do something like that, like putting everything together, you can expect that a fraction of the alum will mordant the fibers, but a fraction of the alum can also interact directly with the mother and form a sort of a lake. And the lake can then deposit on the fibers and form something like this. So again, this is very interpretative. We haven't done an experiment to confirm that this happens or not, but I would like to hear your opinion about this. And this is for the Safflower. The Safflower has this very nice pink-orange luminescence under the UV light, and it's, in this case, it was quite well distributed on the fibers, and the particles that could see were very, very small and more consistent with some residual plant material rather than something more complicated. And this is the LCMS for showing the presence of cartamine for all the Safflower samples. Just to conclude, we tested the analytical protocol on other type of textiles, not just Egyptian textiles. We had a project on Dunhuang textiles in the British Museum, and the multispectral imaging was very, very interesting. In this case, the palette is much broader. Instead of having just 4 sources of colors, we could find around 15, 20 sources, and this is the multispectral imaging was very useful to divide them, or at least have an idea of what was present or not, especially when we were in front of real textiles. So here you can see the luminescence, the yellow luminescence of the Amur cork and the orange luminescence of the Safflower. So we were already identifying at least 2 sources of dyes without taking any sample. But then it was just with the LCMS that we could identify all the sources of dyes, and as I was saying, there were many mixtures, so it was a more complicated data set. We published extensively on the topic as well, so if you want to know more, this is where to go. And finally, we also did something very similar on Pacific bar cloth. And again, a completely different reference materials. The dyes are different, but the approach that you can use from an analytical point of view can be similar. And to conclude, I would just like to say, to re-echo a bit the question that I asked yesterday, that independently on the geographical origin of the textiles that I have analyzed, that we have analyzed at the British Museum, we found out that identifying the dye source is not impossible. So you can have a quite good idea of the source of the dye that was used. But how these dyes were applied especially when they are applied in mixtures, is much difficult to understand from an analytical point of view. Mostly because the analytical techniques have their own limitations, so there is definitely an analytical challenge there, but also because we don't have the people we can talk to today. So 1,000 years ago, these people were doing the same things that the dyers are doing today, so have experimenting, have their own way of, and the curators ask a lot of questions about that, the conservators as well. As scientists, we are a bit stuck. So I just think that the future research should, from a scientific point of view, should go a little bit more in this direction and try to understand, to focus a bit more on the hands of the people behind the textiles rather than the textiles themselves. And so I just would like to thank some of the people who helped in this work and you for your attention. Thank you.